Hi, students. So this is the second half of the second unit. So it speaks about the public key cryptography principles. So part of that, the first one is the Diffie-Hellman. So the public key encryption firstly proposed by Diffie-Hellman in 1976. So public key algorithms are based on mathematical functions rather than simple operations. Public key cryptography is asymmetric, involving the use of two separate keys. So if you use one key, it is symmetric. If you use two keys, it is asymmetric. So what is that you do is here the plain text, the key students, you do the encryption, you get the ciphertext, and you do the decryption with the key and you get the plain text. So here it is mentioned, you can see here public key is there like A, B, C, D, and there is a private key C. So what happens here is the public keys of every user are present in public key register. And if B wants to send a confidential message to C, B encrypts the message using C's public key. And when C receives the message from B, then C can decrypt it using its own private key. Okay, so here you encrypt using public key and you decrypt using uh, private key. So no other recipient other than C can decrypt the message because only C knows C's private key. So that's the main point here, right? The components of the public key encryption is plain text, ciphertext, encryption algorithm, decryption algorithm, and public keys and private key. Okay, so the first algorithm that you'd be seeing is the RSA, Ron Rivest, Adi Shamir, and Leonard Edelman. So the algorithm is proposed in 1977. It is published in 1977. It is an asymmetric public key cryptographic algorithm. And if a person A wants to send a message to person B, person A encrypts the message using person B's public key and person B decrypts the message using their private key. So it is based on the factorization of large number and modular arithmetic for encryption and decryption. It consists of three main stages. First, you generate the key, students. Then once you generate the key, then you do the encryption, then you do the decryption. So these are the steps. This is the only algorithm among the discussed algorithms. Like you are supposed to write the steps here. So without diagram. So step one, set prime numbers. So as part of starting point of RSA, choose two prime numbers P and Q. P is 11, Q is 13. Two prime numbers must be different, P and Q, right? And calculate the keys. So how do you calculate the keys? Is private key n comma D and public key n comma E. Now your job is to identify what is n, what is D, and what is E based on the prime numbers that you have selected, 11 and 13. So 2.1. So how do you identify n here? Okay, n. So calculate n. Simply multiplying P and Q. 11 into 13 is 143 and n is of length 8 bit, right? And the psi function to calculate E and D, the Euler phi function is used. So phi of n is P minus 1 into Q minus 1. So 11 minus 1 into 13 minus 1, that's 120. And the number E can now be chosen freely. However, it must be a co-prime of this, right? That is, this is 120, right? So it's like we here the chosen number is 17. You can choose any. So two numbers are co-prime if their greatest common divisor is 1. And once you represent it like this, 120 equal to 2 power 3 into 3 into 5, the numbers that are co-prime with 120 will not be divisible by 2, 3, or 5. So the numbers can be this, right? Out of this, we are choosing 17. You can choose any number. Okay. And next, the following condition must be met, like GCD of E comma pi of n equal to 1. That is 17 comma 120 is 1. Next, D. The number D is a multiplicative inverse of E. So E into D mod of y of n is 1. So 17 into d mod 120 equal to 1. Now your job is to find the value of d. So if you want to find the inverse modulo inverse of 17 mod 120, then solve the equation 17x plus 120y equal to 1. X will be the inverse modulo and 17 mod 120. So 17x plus 120y equal to 1. So step 1, first division, we divide 120 by 17 and we get quotient and remainder. So 7 is the quotient and 1 is the remainder. Since GCD of 17 comma 120 is 1, we can express at 1 equal to 120 minus 7 into 17. So rewriting this, that minus 7 into 17 plus 1 into 120. So obviously, right? So here x equal to minus 7 and y equal to 1. So 1 equal to minus 7 into 17 plus 1 into 120. 1 into 120 terms is vanished and 120 triple equal to, this is not double equal to 0 mod 120, thus reducing the modulo 120 minus 17 plus 0 triple equal to 1 mod 120, then minus 7 into 17 equal to 1 and minus 7 is the modulo inverse of 17 modulo 120. The modulo inverse are usually expressed in positive integer. So d equal to minus 7 plus 120 is 13. So once you get the value of n, e and d, students, you can represent the public key and the private key. So the n is 143, right? So first represent the private key, n comma d is 143 comma 113, public key is n comma e 143 comma 17. So once you are done, once you identified the keys, do the encryption. To encrypt a number m to a ciphertext c, the following formula is applied. C equal to m power e mod n. So suppose m is 88, 88 power 17 mod 143, that is 121. Once you decrypt it, students, so mi, this is inverse, that is decryption is the inverse of encryption, right? That's why m inverse equal to c power d mod n. 121 power 113 mod 143 is again 88. So this is the RSA algorithm. So RSA algorithm steps is key. First you guys have to generate the key, then you have to do the encryption, then you have to do the decryption. So key generation, how do you identify public and private key is, start with setting the prime numbers, then identify n comma d, n comma e, and then once you are done with the public key and private key, do the encryption and do the decryption. Right? Now, the next algorithm that we have to discuss is the Diffie-Hellman. Diffie-Hellman, students, just a minute. The Diffie-Hellman, and so here you guys have to, just a minute. Okay, so Diffie-Hellman. So the first slide of the two PPTs that I've uploaded, students. This is Unit 2, related to Unit 2, and there's Unit 3 as well. The first slide is the same. So don't just confuse like both the PPTs are the same. Yeah, Diffie-Hellman. So basically, Diffie-Hellman actually works on this principle, paint color mixing, right? So Diffie-Hellman key exchange, right? These guys, the sender and receiver, will be exchanging the keys, students. over a unsecure channel without having prior knowledge of each other. And they never actually exchange the secret, just some values that both combine, which let them attain the same resulting value. Okay, the last one, same resulting value. So just this is the diagram. So Alice and Bob, okay, both have common paint, yellow and yellow. And if you just see the resulted, the common secret. So if you just see the color mixing, students, right? Here you have some colors here. Here you have some colors. So here the color mixing here and here both are different, but they are coming up with a same color here. Okay, if you just see like yellow and yellow, and these two are combined to form this color, and here these two are combined to form this color, and this color is exchanged. It will come to Alice side, this color will come with the Bob side, and this blue color is again mixed with a different color, this color is mixed with another color, right? And both come with one same color. So this is a paint color mixing. The same process applies in the Diffie-Hellman students. So Alice and Bob, first they agree upon the prime numbers 13 and 6, for example. This is a private key 5, the private key 4, right? And once you apply the formula, you will get a public key 2. Here you will get a public key 9, and this is the formula G power private XOR private mod P, right? Once you exchange, like you have exchanged the colors here, right? So same thing. Once you exchange, what you again apply the formula, students, here. See, so private mod P. Once you apply the same formula, you are going to get a secret key, that is 3, and here also 3, right? So the point is here, uh, since the color mixing and the exchange and how the secret key is coming, here it is different and here is different, and the gut feeling is like the hacker cannot get back to the original state, right? So Alice and Bob now have the uh, shared secret key, which they can use to establish a secure communication channel. The security of the Diffie-Hellman key exchange relies on the fact that it is computationally infeasible for an attacker to determine the shared secret key S from the public key values PGAP. This allows Alice and Bob to exchange the key securely even over a insecure channel, right? So that's the advantage here. So the next topic is the digital signature. It's just a mathematical technique used to validate the authenticity and integrity of a message, software, or a digital document. By providing mechanisms for authentication, integrity, non-repetition, these technologies help protect against fraud, data breaches, unauthorized access. So to understand a digital signature, then there will be a message digest computed by applying a hash function on a message, and then message digest is encrypted using a private key of the sender to form the digital signature. Is then transmitted or a message with a message. The receiver decrypts the digital signature using the public key of the sender. The receiver now has the message digest. The receiver can compute the message digest from the message. The message digest computed by the receiver and the message digest. So to understand this, this is the original data, students. You just pass it to an hashing algorithm. You'll get a one-way hash. So use a private key and you do the encryption, you get a digital signature, right? So this is passed over a network here. Fine. And here at the receiver end, students, the original data is sent. Original data is sent to a hashing algorithm, and you get a one-way hash. And here is the digital signature. Digital signature is decrypted using a public key. Here you get a one-way hash. So once this hash and this hash both are same, then the communication that you have done is secure, and then you can start your communication. If this hash and this hash both are different, then somehow the hacker or some modification has done. The integrity is not maintained. Integrity means whatever the sender has sent, the receiver has to receive. So there's no integration. Stop the communication. Wait for the other hash. Okay, that's how you can actually use the digital signature to actually identify the sender, right? And next is the digital certificate. Each digital certificate actually contains the name of the certificate, serial number, expiration dates, copy of the certificate holder's public key, and digital signature of the certificate issuing authority. Every application contains a digital certificate, students. So if you are actually going for a Spring Boot, so once you start building the application, all the related jars will be downloaded. So how they are getting downloaded is with a valid certificate, right? Digital certificate is also sent with the digital signature and the message. So digital certificate, the advantages is there's a network security, verification, and the BIOS success. Okay, and the disadvantage is like phishing attack might happen. Users may be fooled with the sensitive information. Weak encryption. The older digital certificate system may employ less secure encryption. So some of your applications will have digital certificate students with the expiration date. So year is 2025. Application might be using a certificate with the 2024 date, right? And miss configuration in order to, for the digital sector to work, they need to set up correctly, and websites and online interactions can be attacked due to incorrectly configured certificates. So you should have a certificate to make sure that the communications, the the downloads, or whatever the actions that you perform, all those are performed in an authorized manner with proper authentication. If that is the case, then use a correct digital certificate. If you have any expired old digital certificates, please make sure that they are getting renewed with the new date. There's a certificate authority, which actually is a trusted organization, students, that issues the digital certificates to websites, businesses, and individuals. When CA issues a certificate, this is TLS SSL, okay, transport layer and socket layer certificate. It verifies the website domain depending upon the type of the certificate, the organization behind it. Right? If you are able to download something from the website, students, right? If something is getting downloaded, then there is a certificate, and that certificate tells this downloadable action is valid, right? Next, why certificate authorities? Internet relies on encryption to protect the sensitive information or cyber threats. By validating website ownership and issuing this certificate, CS enable encryption between web browsers and servers. The encryption ensures that any data exchange, like login credentials or payment details, remain private and secure. Okay. Next, so certificate authority. So there is a domain validation confirms control over website domain without verifying the identity of the site owner. Organization validation verifies the identity of the business behind the website, providing more trust for users, right? And next, extended validation. So EV certificate offer the highest level of verification, displaying the organization name in the certificate details. So they are used by financial institutions, major e-commerce brands, right? And next, key management. So this is the last topic of the second unit. Key management refers to the processes and procedures involved in generating, storing, distributing, managing cryptographic keys used in cryptographic algorithms. So we have discussed the symmetric key cryptography, asymmetric key cryptography. Symmetric keys have only one key. Asymmetric keys have two keys, public and private. So these are the types of key management: manual key, centralized key, decentralized key, symmetric key, asymmetric key, cloud-based key, hardware, security module key, blockchain-based key managements. So out of this, just learn manual key, centralized key, decentralized key, symmetric key, asymmetric key. You can also learn blockchain-based key as well. So next. So manual key is the keys that are generated and distributed manually. That is the Wi-Fi password, students. They are very simple to implement, but keys can be lost, right? And they can be hacked easily. Wi-Fi password. Next is centralized key. There is a key management server that stores and manages all encrypted keys. Administrators control access and monitor key usage, like AWS, Google Cloud, and it is easy to control and for updating. And single point of failure, if the key KMS, the key management system server, key management server, if compromised, all keys are at risk. So the any symmetric algorithm or the asymmetric algorithm, the main thing actually relies on the key itself. So that should not be compromised here. Decentralized key management. Each system or device manages its own keys instead of central server, often used in blockchain and distributed systems. So initially, blockchain is a centralized system. Students later became the decentralized one. Okay, you can see Bitcoin and Ethereum use decentralized key management for wallets. So no single point of failure. Next, symmetric key management, like we have discussed some key symmetric keys like PES, Blowfish, and IDEA. Risk is if key is stolen, all the encrypted data is compromised. So, like we said, like we are discussing, the main secrecy lies on the key itself. Next, asymmetric key management, where here you'll be maintaining the public key and the private key, like RSA, elliptical curve cryptography, and Diffie-Hellman are the examples. Hardware security, model key management, physical devices that generate, store, and manage keys securely. So used in especially military, banking, and government applications. So example is AWS. So extreme security. So if and it is expensive and complex to maintain because we are telling about physical devices, right? And cloud-based key management, keys are stored and managed in cloud, and cloud providers handle key rotation and access control. So we have like Azure, AWS, and Google Cloud, highly scalable and automated. And this third-party students. So you might have to, you know, uh, have to give access to the keys as well. Blockchain-based key management use decentralized ledger control to store and manage keys. Each user has a unique private key to sign transactions. So cryptos, for example, and no central authority needed. So if you are actually losing that key, permanent loss will be there on the assets in the blockchain students. So the drawback of all these things is whatever the key like asymmetric, symmetric, cloud-based, or you are doing manually, the key should be secure. So this is the key management life cycle. So first you are going to generate the key. Next, install the key, establish the key, then certify that key. Once you got that certification, use that key, save it somewhere. If you want to update and recover that and revoke. When you do the revoke is if you though you are using that key, the hacker is able to find the original plain text, then usage of key is no way required. You can just revoke that key. So all these stages are explained. First is the key generation. Once you generate the key, next is the key distribution. So symmetric keys and asymmetric keys. Key storage. So key must be stored securely. And key usage. So keys are used for their intended cryptographic functions, can be encryption and decryption. Key rotation. Keys are periodically updated to reduce the risk of exposure. Key revocation. These keys, those keys which no longer secure the information, the hackers are able to find out the plain text, right? They are no longer secure and are needed to be invalidated. So key archival, old keys are securely archived for future reference. So the key must be old, but the key must have been highly secure, right? So just save it somewhere. And key destruction, when keys are no longer needed, they are securely destroyed to prevent any possibility of recovery. So this is about the second unit students. Thank you.